Hi. So today I'm going to talk about data structures and various approaches to making them robust. Well, I suppose what I'd really like to say is production-worthy, right? How do you make sure that your data structure is production-worthy when implementing it? But before I get to that, I'd just like to introduce some terms. So what are data structures? Well, data structures are concrete realizations of abstract data types. Now, abstract data types are basically collections of operations that let you construct and interact with instances of those abstract data types and axioms that describe the relationships between the various operations. So, for example, for sets, you could write down an axiom like this one, which says that for any set S, it is the case that for any X, for any Y, the set obtained by conjoining X onto S contains Y, if and only if S already contains Y, or Y is equal to X. And for any interesting ADT, you'd expect us to write a number of these to capture adequately what it's all about. So when you implement a data structure, then these axioms form like the foundation of the contract that this data structure presents to users. But for it to actually be useful, for the data structure to be useful, it tends to be necessary for it to make further guarantees, right? Certain complexity and performance guarantees related to, well, how quickly operations complete, both in terms of the asymptotics and in terms of the performance on real-world hardware, and also things like frugal use of memory, say structural sharing in the case of persistent data structures. So when you publish a data structure, you make a certain promise to your users, and it's a two-pronged promise generally. So one part is that, OK, this thing here, it's a black box that obeys this ADT contract, and then additionally, it is quite performance, and these are the performance characteristics. So it has, in the past few years, become received wisdom in the community, I think, that black box generative tests are the way to go when it comes to verifying compliance with ADT contracts. And I think this is fantastic, and this is totally the way to go. Like, even if you go to the trouble of formally verifying correctness, you still want some tests, and generative tests are the best kind when it comes to data structures and to things like the axiom above. And then obviously with the data structure in hand, you always need data. You always need benchmarks, right? Some real-world, or well, reasonably close to real-world information on how it actually performs on actual hardware, on an actual JVM, and so on. And if you have a robust and rich enough suite of benchmarks, then you can get some information on whether the actual behavior of the data structure matches the promised asymptotics, say. It's a very coarse-grained thing, though, and to make it less coarse-grained while keeping the black box nature of it, you'd have to make it just extremely extensive. It would take ages to run. It's not very practical. Now, in this talk, I'd like to make a case for white box testing, generative testing of data structures as a way to verify internal invariants that back the performance guarantees of data structures. And I'd like to suggest that it is crucial that in addition to our black box tests, we also build these white box tests, and that they can provide good value, and well, and it will turn out at some point in the presentation that spec can be useful when doing that. But before we get to that, I'd like to just give you a selection of interesting bugs that came up over the past several years that I found particularly inspiring and that, that kind of led to all this. 3 in total. There are 2 items here, but one of them actually hides 2 bugs. So, OK, so let's move on. The first one was reported in 2013 by Zach Tellman. And well, basically, this is how his collection check library burst into the stage, right? Screaming, oh, I found a bug in your persistent hash maps, right? So that caught my attention, certainly. So the story there is that when Rich first developed persistent hash map, it was a persistent-only data structure, right? Transients are a later addition to Clojure. And so, so when it was first implemented, the persistent hash map was free to make certain assumptions about the internal structure of its nodes. That it turned out the later addition of transient hash map invalidated. And the thing is, some of those cases were actually missed and were only discovered by a generative test. Once discovered, this was reasonably simple to diagnose because you could get at an actual problematic instance very quickly just by following the output of the generative test, and fairly straightforward to fix. Well, it was very striking, right? Like you could go for several years, I think, with bug in place that is just that had the property that you had to be somewhat unlucky to run into it, and then you know if you run into something weird once in a blue moon, you might not even think that it's necessarily a bug. So, okay, so that made it clear that that generative testing is the way to go, and it made it clear that collection check in particular is a great library to use. So, here's the commit message for Christoph fixed the bug. So when I developed data.avl in 2013, well, I didn't have this sort of test suite in place initially, but in the early days of January 2014, with this early collection check success fresh in my mind, I knew I wanted to have this kind of thing in place. So I wired it in. Actually, before Christoph's patch was even made it into a released version of Clojure. And just to give you some background on this library, because I'll be using it for various examples throughout the talk. What data.avl is, it's a contrib library. It implements drop-in replacements for closures and Clojure scripts, sorted maps and sets, with a richer API, right? So they support the transient API, and they also support a bunch of operations like nth and rank off, which is basically the reverse of nth, nearest neighbor lookups, and splits, which are like Clojure core split ads, but they return subsets or submaps. And subranges is similar to subseq, but again, it returns a subset or submap. Well, with collection check in place and obviously various other tests, I was reasonably happy with the robustness of that library, and it's awesome early use, and it's and well, okay, so it was good to see it actually being used with collection check in place. I felt that, well, okay, so surely at least the map API is fine. So yeah, I was feeling pretty good about this one. Until August 2016, when a bug report landed. It was submitted by Dirk Weber, and I'll quote his description. When I split the map and then try to split again on the right result, the split fails to return results. Well, so I conducted an investigation, and again, well, he was kind enough to submit a patch with some generative tests that are now part of the test suite and will hopefully prevent any regressions here. But with those generative tests in place, it was actually fairly simple to pinpoint the problem and fix it. I'll quote the post-mortem that I published after pushing the changes. The root cause is that as of 0.0.13, node ranks get miscalculated in one of the cases in split. Ultimately, this means that it is possible to construct a map that actually holds the expected entries, but whose count is less than it should be. Well, so that was really, really unfortunate. And the reason it took a while to discover is perhaps that it was possible to use data.avl in such a way that you'd get a value out of it, but never observe this particular breakage. Because of, I guess, the way in which various features interacted. So this got masked in some cases. It wasn't relevant to certain types of users, but still, it was a case of a completely broken contract, right, for one operation. Well, I didn't get to it right away, but at this point I started thinking about and then got distracted in various ways. And eventually I got around to putting together a new invariant test because I just didn't want any of that. So I decided that, okay, well, it's time to reach into the internals and verify that randomly generated instances obey all the invariants that I expect them to obey, because, well, if I know that, then surely it will then be possible to trust the library to work correctly. And, well, I was kind of expecting to just put them in and reassure myself that everything's fine and move on, right? What happened instead was that I put them in and discovered that everything was not fine, then fixed the bug, and then felt reassured and moved on. But the thing is that the problem that these new tests uncovered is something that there's very little chance of a user observing, because the thing that was broken was well, I guess one of the cases. I'm not sure if it was just one, but there was a scenario in which you could perform an operation, an update operation on the tree, an assoc or dissoc, and it would be performed correctly in the sense that the binary search tree would hold the expected entries at the end, but the rebalancing step would actually not be performed. And so you could find yourself in possession of a purportedly AVL tree that actually no longer obeyed the AVL invariant, and if you happen to make multiple modifications to a problematic fragment of the tree, well, maybe you could observe some operations behaving a little, more slowly than you'd expect. Nothing would visibly break, but it's still not something that should happen, and it still compromises performance guarantees for certain user patterns, at least. So obviously, these invariant-oriented tests are in place now, and hopefully they will prevent regressions. We'll see. But the main point I want to make is this kind of thing would not have been caught with collection check or anything like that, right? Because in no way did this break the observable contract, right? You had to reach inside. So around the same time, I was implementing priority search queues for closure. And I actually presented this library at last year's Euro Closure. It's called PSQ CLJ. PSQ stands for priority search queues. And to give you some context, they're basically sorted maps when you look at the keys, but then with respect to the values, they behave in a priority queue-like fashion, and then there are some operations that bring the two aspects together. So when developing this library, I had a satisfies invariant predicate in place right away, right? It's there in the initial test suite. And I still use collection check with that. Well, I mean, I use collection check to validate the black box contract. But then I also use some of the internals of collection check, some functions that are marked private that allow me to construct instances, nicely randomized instances of my priority search queues that I can then subject to further PSQ specific operations and check whether the results returned satisfy the invariant I'm interested in. That's a total of, like, I think 54 generative tests in the test suite, and 14 of those maybe use satisfies invariant. And having that in place early on was fantastic. I didn't end up breaking the invariant very often, but when I did, I found out right away it was a great development experience. So at that point, I knew that, OK, well, going forward, whenever I implement a data structure, this is what I want to do. The only question is, well, can I do something better? Can this be improved? Is it possible to build better tools to facilitate this kind of testing, and so on? So this is basically what the talk is about. Oh, and the expression on this slide, I don't really recommend reading it here, but it's just the main end expression in that satisfies invariant predicate. So it's basically a huge let form, and then this is its body. So the situation now is that we have a bunch of data structures, right, whose invariants are being tested in a white box fashion. I mean, we reach inside and check that everything's fine. But the instances which we subject to these checks are still black box generated, in the sense that we call functions in the public API, typically starting with an empty instance, and building up large instances. Well, not just large instances, just more instances with more complex histories, right? We might assert some keys, disassert some keys, conj some entries, and so on and so forth, and then at the end, maybe do a split or whatever. PSQ-CLJ supports the entire data.avl API for its sorted map aspect. So there's a number of operations to then apply and test and for invariant preservation. And I would say that this is actually quite good when it comes to providing guarantees related to the ADT contract mostly, and also some guarantees related to the data structure contract. When it comes to the shrink-wrapped package, right? When I put out this package, this library, oh, here's a library that does this. With this kind of test in place, it's reasonable to feel somewhat confident, particularly if you actually read it and run it for yourself. OK, well, it probably does work as advertised, right? Because it's all being checked. But there's actually at least one more thing we could try and accomplish using this kind of test suite, and that is a deeper understanding of the implementation, right? Suppose you want to evolve it. Suppose you want to build a more complex data structure, taking an existing data structure as a starting point, right? Then it is really necessary to understand the thing that exists so that we can build this other thing that we want. Also, when designing tests for an implementation, you really do want to have intimate knowledge of it. Well, these white box tests, at least. So maybe we can still do better, so that we can offer even better guarantees for the shrink-wrapped package in terms of our ability to say, explain to the users exactly what the data structure does and how it does it, and what it can be used for if you're prepared to maybe modify it and so on. OK, so at this point, finally, it's time for spec to come on stage. Now, I will say up front that it doesn't seem at first glance to be useful for validating low-level invariants. Now, it is protocol-based, so I can imagine maybe trying to make it directly useful, but I actually didn't feel like doing that so far. Because it's also possible to just build map-based representations of your data structures, right? Like, say, if data.avl has a number of def types which have certain fields, and then once you descend into the fields, well, some of them hold further instances of further def type introduced classes. Well, here we can just have maps, right, and keys in those maps that correspond to fields. And then with that map-based representation, it's possible to do at least two things. One thing is that you can actually implement all the relevant operations using that representation. and this can sometimes be useful. But the other thing is that you can provide some conversion functions that take well, actual, say, data.avl maps and nodes and convert them to map-based representations of AVL maps and nodes. And then there'll be a second pair function that converts them back, right? So both approaches can make sense, but particularly the latter is relevant when testing the actual implementation, right? So that's what I'm mostly going to focus on. Now, what you want to do with the map-based representations is you want to spec them, and you want those spec to capture all invariants that you care about. So, for example, well, we'll get to some examples in a minute, but things like AVL invariants, like binary search invariants, and so on, you want to capture them using specs, and you want to make sure that you can then generate instances that satisfy the invariants using the generation machinery in spec and test.check. So to that end, it is likely that with-gen will be necessary. You want to provide custom generators because, well, first of all, you're likely to have to deal with some classes that spec doesn't know how to generate. Say, comparator is one such class. But then also, if you have complex invariants that span multiple fields, well, or just complex invariants really, then spec won't just be able to understand them and magically generate precisely the instances you need, right? It'll keep trying, and in principle, it would eventually succeed, right, if you gave it infinite time, but in practice, it tries 100 times and then gives up. So you can start with very naive generators, but oftentimes it is necessary to tweak them. But what's nice about this, though, is that the fact that spec keeps trying, like when you register a generator for a spec foo and then attempt to use it, then it won't just give you back whatever the generator generates. It'll give you back the things that the generator generates, but only if they obey the spec, right? That means that you can use overbroad generators that do generate some malformed instances, because it's sometimes just easier, right? Easier to accomplish good coverage in this way. So that's a balancing act, but it is a very useful facility. And finally, what's nice about this whole setup, once you build it up, is that potentially it may be able to generate unreachable instances, meaning instances of the data structure that obey all the invariants that you thought about, right, and that you expressed in your specs, but nothing else, right? And so conceivably, you could get instances that you couldn't even reach using the public API, right? And I think this is good. I mean, this is amazing, because once you reach such an unreachable instance, two things can happen, right? Like you can apply some operations to it and discover that, okay, well, the operations now go crazy because this is not something that the data structure is prepared to work with. And that's good to know, because that means that you don't actually know what the invariants are, right? Clearly, you rely on some invariants that you have not yet made explicit. And then the other eventuality is that everything's fine, right? And then, well, if everything's fine, then that's also an interesting thing to know, because, well, maybe you want to build something on top of this data structure. Maybe these unreachable instances will somehow become relevant. So the ability to make that possibility explicit is great, I think. And just to give you an example, of what a spec'd data structure might look like. Well, here's a few things I built around data.avl. So there are two main specs. There's a node spec and an avl-map spec. The division of responsibilities is that node checks heights and ranks, and also the AVL invariant. Whereas AVL-map is responsible for checking that count matches the actual node count in the tree, and also that the tree is actually a binary search tree. Now, it might seem like that should be the responsibility of Node, but there are several problems with that. One is that, well, you would have to provide your comparator to the node spec, first of all. No way to avoid that, which would be fine, but it would mean that that your map-based representation would be won't be as close a match to the actual low-level implementation. So there's a bit of a trade-off there. But in any case, it is much more straightforward to handle generation at the top of the tree, because when trying to generate a binary search tree, I find at least that it is easier to generate the shape of the tree and the keys to be inserted into the tree separately. So you generate the shape, and then you put the keys in the right places in order, right? So it's straightforward to do it once at the top and to not worry about key order in Node. I do have a separate spec for actual BST nodes that's separate, and that actually calls on the generator of avl-map to handle its own generator. So it's useful in a number of tests. And now I've experimented with a number of specs for keys and values. Just to keep this simple for this talk, I included the simplest ones I used. They're actually good enough, because using just integers for keys well, kind of seems restrictive. You want to do more in a proper test suite, but at the same time, just for like with a black box test suite in place, you kind of know that the data structure basically works. So then it's reasonable to use a very simple domain for keys when validating some structural invariants. And what it also does is it keeps things a little shorter, which makes it possible to just about fit them on slides, which was also important. So this is what Node looks like. And it isn't really necessary to read this. I'll just comment on a few crucial details. So first, there's an S-key spec that checks that the right keys are present. And left and right just resolve to Node again. So your subnodes are validated, which means in particular that you can rely on their heights and their ranks being correct. And there's a bunch of predicates. There's consistent height question mark, consistent rank question mark, obeys AVL invariant question mark. These all do what you expect. And finally, there's a generator. The generator is a custom function that I don't think I have it on the slide. But what it does, or what this iteration of it does, is it interprets its size parameter to mean the height of the tree that you want to get. Now, an AVL tree of 100 million items might have a height of 27, say. So you can't realistically generate very deep trees, right? So it is important to apply the right kind of scaling. This may not yet be perfect, but it's reasonable. avl-map is spec'd in this way. This is the wrapper object in data.avl. So there's a comparator, which is just a comparator. There's a tree count and a meta map. I left out hash values for this set of examples. We check that the tree obeys the BST invariant using the comparator in the avl-map wrapper object. We check that the actual node count in the tree matches the count specified in the wrapper object. And we're done with the spec itself. The rest of it is the generator, which does a number of things. But you'll notice that it's possible to reuse generators for various specs that are relevant here by calling sgen. So that's quite nice, and well, I think it keeps it simple. And finally, with these things in place, what you can do is you can write a custom property, custom test check property that well, maybe I'll go through this, that generates a map-based representation of an avl-map, which is well, probably reachable. I don't think there are any unreachable instances in data.avl, but if there were, then potentially you'd get one of those. Then there's a call to a collection check internal private function that generates map-oriented operations. And with these two things generated, we convert the map-based representation of our avl-map into a proper avl-map. We apply another private collection check function to build up a more interesting avl-map. And then we convert it back to a map-based representation and check that it satisfies the spec, meaning that it actually obeys all those invariants that we previously thought about. And obviously, we do rely on these conversion functions for correctness. But well, they can themselves obviously be generatively tested, and that's rather straightforward. So they're also extremely short and simple functions. So it's reasonably easy to trust them. Yeah. So this is actually quite good already, but it turns out we can do better. The way I discovered that we can do better is that again, before I was done with this, I re-implemented as an experiment the key features of data.avl using the map-based representation. Actually, well, to say that I re-implemented them is maybe overselling what I did very slightly, because I took the existing implementations, just converted them to use the map-based representations. And then I started adding specs, function specs, and using closure spec test checked to test them. And it turned out that, well, okay, so what I got was a bunch of test results, most of them successful test results, but some of them, including some failures because of a typo here or an omission there, or what have you. With like the core message equivalent to what for all would tell me, like, okay, this thing broke, right, and this is the input that broke it. But then I'd also get a full spec message pinpointing exactly what broke, right? Like, this thing broke, and this is how, right? This is the specific predicate that that it didn't satisfy. So that's fantastic. So I then turned around and applied the same test, basically, to the actual data.avl functions using those conversion functions as sort of sandwiching layers. And OK, well, I got the same results, actually all passing results, if I remember correctly. And now I have to say that, like, I don't want to make a statement that I don't fully believe in. So I'm not going to say that this is something that can possibly be done without spec. But it's similar to, I think, this year's Closure West, Daniel Solano Gomez had an amazing presentation about tackling a legacy system that they wanted to replace using spec. I think he made the point that, OK, well they use spec because it seemed interesting with this nice new tool. And they're happy with it. Obviously, in a different language, you could not have access to spec. Then maybe you'd use something else. You could also conceivably just build your own machinery. But the thing is that the tool worked, and it has a number of features that come together in nice ways. So I think this has also been my experience. With something like spec available out of the box in Closure, I don't feel terribly inclined to build my own thing, because this actually works very, very well indeed. Now, once you do this, right, once you provide check-based tests for all your internal functions, what becomes clear is that function specs could actually be used to improve on this thing. And the way to do this is, well, suppose you want to make sure that the split key operation in data.avl, which takes data.avl map or set and a key and returns a vector of a subset or submap of the input set or map that includes the keys less than your key. That's the first item in the vector. The third item in the vector is the same thing, but on the right side. And then the middle item is nil if the key, your split key, is absent from the collection, and it is the map entry or the key itself in the case of a set if it is present in the collection. So suppose you want to make sure that if given an arbitrary data.avl map or set that obeys all the invariants that we know about, split key produces correct AVL maps and sets that also obey all invariants that we know about. Well, you can write a helper function that takes as inputs the things that you expect to generate for a test that will check this. And in this case, you want a starting point, so basically a starting like a seed AVL collection. You want some actions to apply to it using collection check perhaps, or some other operation runner. And you want a split key. And then you build a bunch of data structures, right? You actually apply split key to an interesting AVL collection. You also maybe take some seeks over the relevant data structures. And then you return all these things in things of interest in a vector or a map or whatever, some sort of data structure. And then you provide a spec for it that actually doesn't even need to use the FN part of function specs, because it ends up being the case that the red part already captures the relationships of inputs and outputs, because well, the way at least I approach this, the relevant inputs are just included again in the output. And your arg spec handles generation, obviously. So AVL0 will be an AVL map, an initial AVL map. Split key will be an arbitrary key. And actions, well, the spec I use for actions is called CC editable sorted map actions, which means that it's a collection of, well, a sequential collection of actions applicable to transient-enabled sorted maps generated using collection check. Yeah. So that's what your function takes, and then it outputs a sequential data structure that includes an AVL map, then another AVL map, possibly an entry, a map entry, and then yet another AVL map. So this L AVL, E question mark, and R AVL parts, these are the output of split key, and a few additional data that are useful for validating things. And it checks that things behave as expected. Actually, I think I put a shorter version, like a short initial version on this slide. The version that I can't use has one more branch in the end. So if you actually read this and spot that something's missing, well, it's probably there locally, but this way it fits on the side. And to run the to make this into an actual test, you do something like this. Like this is a successful check predicate, because the check function returns a map that describes the result, and you have to fish out the actual true or false, or maybe it's no, that tells you whether the test was successful out of it. So that's just a function that does that. You run your test 50 times, and well, if it breaks, then you get a really nice description of exactly why. Actually, the way it's written here, you probably don't, because the predicate masks it. But if you run the check expression in REPL, then you do. Okay, so I actually covered all this, and I would say that I haven't experienced too many impedance mismatches when working with spec, applying it to to data structure invariants. There are some. The main one is that there's no way to parameterize specs, right? So if you have a spec, say, for a recursive structure, and you want to validate your parent node based on, your child node based on some information that's explicitly available in the parent node, well, then you can't, right? You have to work around that somehow. And there's a number of ways to work around this problem. Sometimes it makes sense to just make information explicit. That would ordinarily be implicit in a low-level implementation. I found that to be entirely appropriate and even helpful with vectors, but not so much with binary search trees. And you can also validate things closer to the root of the tree and just validate the whole thing in one go. That trades away some of the benefits, but you still get to keep them elsewhere. So it's mostly okay. I'm not actually completely sure what I think about this, but this is just something interesting that feels like a feature that would be nice to have. But then I haven't actually run into a case where it would be strictly necessary. So and it's been stimulating having to deal with this in a number of cases. So it's maybe it's a blessing in disguise, but I don't know. So at this point, what I'm convinced is the case that anytime I implement a data structure again, this is the kind of test I want to put in place, in addition to all the black box testing that you would expect. And there's a number of data structures that are interesting, so I've begun sort of cataloging the various invariants, and that's very much work in progress. I might someday put out an artifact called invariant catalog, say, or maybe not a single one, but we'll see. Certainly, when I implement my own data structure, they will be accompanied by tests like these, and I have several in the pipeline. So who knows? It'll be interesting developing something using this methodology. And what also occurs to me is that data.avl is currently on version 0.0.17, and now I feel almost justified in believing it to be correct and just done, right? So I don't know if I care about the version number, but I'm told that two leading zeros maybe send the wrong signal. So I just might celebrate Clojure's 10th birthday by bumping the version number all the way to 0.10. So possibly expect this in October or so. And yeah, but for today, that's all I've got. So thanks very much.